Right, let's jump straight into it. Welcome site engineers and students. Today, I'm putting on my Senior Quantity Surveyor hat to bring you a masterclass on bar bending schedules, or BBS, and project cost control. We're breaking down BBS to bill, accurately calculating steel tonnage. You see, this isn't just about bending steel on site. It's really about protecting your project's financial lifeblood. So let's get into it.
We have to start with a hard truth here. Poor detailing and ignoring tolerances in your bar bending schedule, it doesn't just waste a little bit of scrap steel. It literally bleeds the project budget dry. When you miscalculate a required bar length or just kind of shrug off specific bending tolerances, you aren't just paying for the extra material. You're paying for the rework, the agonizing delays, and the whole cascading chain of errors that inevitably follows.
So here's our roadmap for this explainer. We're going to cover Section 1, the cost of mistakes, Section 2, the golden rule of d squared over 162, Section 3, accounting for lapse and waste, Section 4, a beam calculation walkthrough, and finally Section 5, precision prevents overruns.
Starting off with Section 1, the cost of mistakes. We need to protect the bottom line.
As a site engineer, your BBS is your primary risk mitigation strategy. And believe it or not, it all starts with just one number, 7850. To actually control costs, we first have to speak the supplier's language. Suppliers, well, they don't care about the total linear meters of steel you need. They measure and build by weight. We bridge that gap using the standard density of steel, which is exactly 7850 kilograms per cubic meter. Literally everything we calculate hinges on this constant.
Moving right along to Section 2, the golden rule, d squared over 162. This is all about steel unit weight.
Translating that standard density into a practical, everyday site tool brings us to the single most vital mathematical formula in your entire arsenal. You absolutely must memorize the d squared over 162 rule. It is the absolute foundation for estimating the exact tonnage you're going to need to order. In this formula, d stands for the diameter of the steel bar in millimeters. By squaring that diameter and dividing it by the constant 162, you get the exact weight of that steel bar per meter in kilograms. It elegantly simplifies what would be complex volumetric math into a rapid, on-the-fly site calculation.
So how does this actually play out in practice? Well, if we plug 1 meter lengths into the formula, we get standard unit weights. Take a 20 millimeter bar, for instance. The math tells us it weighs 2.469 kilograms per meter, meaning a 1,000 meter run of 20 millimeter bar will hit your budget for exactly 2,469 kilograms. No more, no less. If your length calculations are even slightly off, this multiplier is going to punish your budget instantly.
All right, on to Section 3, accounting for lapse and waste. Time to face the physical site realities. Now, we have to transition from the absolute perfection of a paper design to the harsh physical realities of actual site execution. You know as well as I do, steel doesn't come in infinite lengths. The standard delivery length for a rebar is exactly 12 meters, or roughly 40 feet. But what happens when your continuous column reinforcement calculation demands, say, 15.945 meters of steel? Well, you're forced to overlap two separate bars to bridge that distance. This means you must explicitly account for lap lengths and cutting waste directly in your schedule.
And these are your non-negotiable rules for lapping. First, your standard column lap length is typically 50D, meaning 50 times the diameter of the bar. Second, laps must never, ever be parallel. They should be staggered and alternate to prevent creating a localized weak point in the structure. Finally, labs should generally be positioned 75 millimeters above and below the center line in the middle zone. Getting this wrong doesn't just compromise the structural integrity, which is absolutely crucial, it drastically inflates your required tonnage by adding completely unnecessary steel.
Now for Section 4, beam calculation walkthrough. Let's do some reverse engineering.
Let's apply these strict rules to a concrete example and literally reverse engineer a structural beam. When analyzing the basic parameters of a simple beam, we need absolute pinpoint precision when calculating the cutting lengths. For a simple beam setup, we have to isolate and calculate the cutting length of the top bars, the bottom bars, the exact number of stirrups required to hold them all together, and finally the cutting length of each individual stirrup. It's like putting together a giant puzzle.
To extract our totals, you've got to methodically step through these formulas. For the main bars, you take the clear span of the beam, add the development length, often assumed as 50D, on both sides, and crucially, subtract the 25 millimeter clear cover on both ends, so your steel doesn't just poke right out of the concrete. For the stirrups, you calculate the perimeter,
add your 90 hook lengths, and subtract bend deductions, like 2D for those 90-degree bends. It is a strict game of precise additions and subtractions.
And this brilliantly illustrates how a theoretical diagram translates directly into the final schedule table. It becomes clear how the detailed beam zones map straight onto the schedule. By meticulously applying those formulas we just talked about, we get the exact cutting length in millimeters, which we convert to total meters. Then, we use our trusty d²/162 rule to find the precise total weight of our stirrups and main bars right down to the decimal point.
This brings us to Section 5, Precision Prevents Overruns. Let's talk about why precision matters so much.
Okay, I really need you to listen closely here, because this is exactly where junior engineers make mistakes that end up costing millions. As we saw in our beam calculation, a standard wastage factor is almost always added to the total calculated weight of the rebars. That accepted standard across the industry is usually 3%. But hey, 3% is a whole lot of steel if your base numbers are wrong to begin with.
For a single detailed beam, our precise calculations gave us a base weight of 263.09 kilograms. Adding that standard 3% wastage factor adds almost 8 kilograms to the grand total, bringing it up to nearly 271 kilograms. And remember, that is for one single beam. Now just imagine multiplying that 8 kilograms of waste across the hundreds or even thousands of beams in an entire high-rise project. Mind-blowing, right?
This right here is why precision matters. A tiny miscalculation. Maybe you used 40D instead of a 50D lap length, or you just simply forgot to add the 90 hook length for your stirrups. Well, it doesn't stay tiny. It spreads like wildfire and multiplies across thousands of bars. Honestly, if you have even a 1% mathematical error in your underlying schedule calculation, that compounded tonnage will result in a massive, massive budget blowout before the concrete is even poured.
So, I'll leave you with this. Take these formulas. Drill the d²/162 rule into your head, respect the standard delivery lengths, and always honor your 5D laps. But most importantly, ask yourself this critical question before you ever submit your next bar bending schedule. Is your schedule protecting the budget or bleeding it? Thanks for walking through this explainer with me today. Stay sharp, and I'll see you on site.